Hello everyone, my name is Gavin Santizo, and this is the presentation for our autonomous RC car Interior Design 2 with Dr. Raza. The objectives of this project was to create and design a RC car that can autonomously drive itself using a track that we create with our Hector Slam algorithm and creating waypoints for the car to follow along. Our other primary objective was for it to drive around the track as fast as it possibly could, and to show that we have met our primary objective, we wanted to complete our lap time in under a minute. Our final goal is to have our RC car drive fully autonomously around the track in Lee Hall within a reasonable amount of time, which we determined to be less than a minute for our track or for our lap time. And then a shortcoming of ours so far was that we were not able to implement a system to allow for the car to avoid dynamic obstacles, but it does follow the track and it does follow it quite well. This is a picture of our RC car. So as you can see right here, this is our LiDAR. This is a Hikoyo LiDAR. It is quite nice LiDAR to say the least. This is our NVIDIA Jetson 2. This is the brain behind the operation. This is our power board right here with the antennas that connect to the Jetson itself. A USB breakout board, which underneath the car connects to our VESC, our battery, our motor, and our servo that does the steering is on the vehicle as well. This is the block diagram of everything I pretty much explained. The brushless motor is then controlled by the VESC. VESC also connects with the servo motor that can control steering. This connector right here is what connects the battery to the VESC and to our power board. The power board then powers the Jetson and the LiDAR via 12.5 volts. And then the USB hub is connected to our wireless controller that then operates and moves the vehicle whenever it is manual mode. This is our network diagram. The internet that we use is EduRoam, and then we use WLAN 0 to connect to a laptop running VNC client with the Jetson running a VNC server on it. And then the Ethernet that connects the LiDAR uses the IP address given below, which is 192.168.0.10. So hardware design. The battery is rated for 5.5 watt hours. In total, the car takes up 35.625 watts. So we're given about 1.5, 1 and 1/6 hours. We use a Traxxas DC motor 3351R. It has a total a max RPM of 50,000 RPM. A continuous current of 50 amps and maximum current at 100. Since it is a brushless motor, it does have poles, and it is a 4-pole brushless motor. This is the LiDAR that I've been discussing, the Hokoyo UST10 LX. It has a range of 0.06 meters to 10 meters, and it has a 270-degree field of view. And outside of that, we will go into our power budget. So all of these numbers have been gathered through either data collection or through their data sheets. The VESC has a function that allows for us to track the current draw of the VESC throughout the time of the car running. We determined that the constant current rate when the car is running at 10 miles per hour is 1.5 amps. So that is what our amperage value is for the VESC. LiDAR, this was given to us in the data sheet. Power board, the main component that is driving the power board is the DC to DC converter. It takes 11 or 9 volts or anything from 9 to 24 volts and changes it to 12.5 volts. But the data sheet said that the max current rating is 1.5 amps, so that's where we got that number from. And then the Jetson, we actually had to work backwards. So we knew it on the data sheet, it says how much power it is given, and we know how many voltage or how many volts we are supplying to it. So we worked our way backwards and got our current value from there. The battery itself, um, we had to work backwards from as well because we had the watts. We knew the voltage that it was, so that's how we got that current value. This is our total power consumption with all of the components right here. So we have a little bit of power left over in our power budget, but not too much to where it is overwhelming. Hardware design in relation to the mechanical side of things. This is all the math that we did to be able to determine our initial drive gear ratio, our final drive gear ratio, and then our final gear ratio total. We are also able to determine wheel speed and RPM, our vehicle speed in meters per second, and then we convert that meters per second into miles per hour. PID control. This was a big portion of this project in relation to the Traxxas motor that we discussed earlier. I'm going to go ahead and play this video to show you guys the PID control that we have on the motor. We decided to tune the motor at initially when we started this project, we wanted to be able to tune at every RPM level and have different KP, KI, and KD values for each RPM, or every 1,000, every 2,000 RPM, and have almost like a engine like fuel mapping table sort of. But we were not able to create a function in the VESC software for us to be able to do that. So we had to tune our VES or tune our PID at a specific RPM value. And we decided that the middle ground that we would do it at is 10,000 RPM. So that is what this is showing.
These pieces together. Hey guys, this is Ben Freibush, and today I'm going to go over the software design. So to make all this work, we need a few key things. Firstly, we need a computer on board. So we're going to be using an NVIDIA Jetson TX2 running Ubuntu Linux 16.04. And we're also going to use a VNC server on the Jetson for remote connection to the car while it's driving. So we'll also have a VNC client on a host computer. And then we'll have a few more other software packages. So running a pure pursuit algorithm, and then we're running ROS Kinetic, and we'll get into what ROS is and why it's so important for us. And then we have a controller, so it's a Logitech F710, and we can control the car with that manually. So what is ROS? ROS is Robotics Operating System, and it's really an architecture for data communication between programs. So you can imagine that we're running a lot of programs. We have a lot of data we want to share between these programs. And ROS provides a pretty easy way for inter-process communication between these programs. And it also includes some data visualization tools and simulation tools. So really the idea of how this architecture works is you have a ROS node, and it's basically a program. And it's a program that can publish and subscribe to a topic. And a topic is really a data container. So these programs will either subscribe to data or they'll publish data. So for our really how we accomplish our goal of autonomous driving, there's a few steps we need to incorporate. So firstly, we need to generate a track map, and then we'll localize the car to this track map. And then to traverse itself autonomously, we're going to generate waypoints along the track, and then we'll have the RC car follow these waypoints. And the key is we need to follow these waypoints in an effective manner. So the first thing we want to do is generate a track map. And we're going to do this using a simultaneous localization and mapping algorithm, specifically Hector Slam. So Hector Slam will build a map for us using only LiDAR scan data and no odometry data. And this simplifies the process of obtaining a map for us. So this video right here shows the real-time visualization of us generating a map. So on the left, you can see the blueprints of Lee Hall. That's the location where we test. And on the right side, you'll see the actual generated track from Hector Slam. And that video is, of course, sped up. So now that we generated this track map, we want to localize the car to the map. So we implement a particle filter algorithm for this. And really, a particle filter algorithm is a statistical method of estimating a new state given a previous state and inputs. So the inputs we have for our particle filter algorithm are an initial pose estimate from the user. So the user will select where the car is in relation to the track. We'll take in LiDAR scan data, and odometry data. So odometry data in this case is wheel speed and steering angle. And then the output of this particle filter algorithm is an estimated pose of the vehicle. So where it thinks the car is in relation to the track. So we can localize now, and of course we have a track map. Now we want to generate the waypoints along the track map. So waypoint it's simply the pose of the vehicle at a specific location around the track. And we'll generate these waypoints by recording pose data while driving the car around the track. So once we have these, we want to follow them. And to follow them effectively, we need to follow them in a smooth manner, and we need to control the speed depending on if we're approaching a curve, for example, or if we're on a straight. So to follow these waypoints, firstly, we need to calculate a steering angle to get to the waypoint at a certain look-ahead distance. So the math behind this really it's a big culmination of trigonometric identities, but the idea is we're looking ahead a certain distance from the car at a point we want to go to, and we'll calculate a steering angle to get there along a circular arc. So if you look at the bottom left image, you'll see the effect of increasing and decreasing the look-ahead distance from the car. So if we have a small look-ahead distance, for example, a small look-ahead distance to a waypoint in front of us, we can see the effect of the oscillation that the car will have when trying to traverse to that waypoint. Now, if we increase the look-ahead distance to a large value, we see it traverses that arc in a much smoother manner, but it tends to overshoot. So it might overshoot the turn, for example. So really, we have to find the balance between look-ahead distances to get the smoothest driving possible without hitting a wall. And for speed control, what we do is we look ahead at 2 points, so two waypoints ahead of the car at a certain look-ahead distance, and we calculate the steering angle between these two waypoints. And if we see an increasing steering angle, for example, we know we're approaching a curve, so we want to decrease the speed of the car, and vice versa if we're on a straight. So here's a flow chart of the entire speed control algorithm. Here's our software flow chart. And really, this is encompassing all the programs and data that's used for autonomous driving. So just for an example, here we can see this particle filter node. So really, this is just our program. It's our particle filter program. And we know it takes in a few inputs. So this initial pose estimate, it takes in LiDAR scan data, and it takes in odometry data. And really what it does is it spits out this estimated pose down here. And this estimated pose can be used in our pure pursuit algorithm. So really we're able to visualize everything in action here, which is also helpful for debugging. So now that we have all the pieces of software together, we can actually perform a live demo of this. So in the top left corner, we'll see all the softwares in action. So we've generated our track map. We're able to localize the car, which you can see by the red arrow, which indicates the position and the pose. And then these yellow lines, really, if you look closely, they're yellow dots. Those show the waypoints that we're going to have the car follow. So unfortunately, the video gets a bit laggy, at least the top left corner does at times. And that's really because we're losing Wi-Fi reception in some parts of the track. So sending data to the VNC client gets a little bit laggy. But the GoPro footage, of course, doesn't lag. So you'll see smooth driving from the car. So notice how the car slowed down on the turn, and that indicates our speed control.
Hello, everybody. I'm back. It's Gavin again. So these are the results from our project. We were able to fully generate a map of the track by generating a Ross bag with Hector Slam. We showed a video of that earlier as well. Our car is able to follow waypoints throughout Lee Hall, which is quite cool in my opinion. And then the car is able to speed up on straightaways and slow down dynamically in cornering. We are going to be able to show you a full video of us having that work here in a second. We are also able to effectively generate, like I said, map and Lee Hall with waypoints for the car to follow. Some bottlenecks that we ran into, or some challenges, was organizing a busy schedule. There are four of us. We are all EE students, or all EE or Compy students, excuse me, and every single one of us have work or extra schoolwork outside of this class. So it was a very hectic semester for all of us, but we were able to get it done and get it done well. We also had to fight to figure out what parts were compatible with the project and what was not. And then algorithms, we were not able to find all of them quite well, so we had to tune and mess with them quite a bit to be able to get the car working and working properly. Some future directions for the project would be to improve the peer pursuit algorithm to be able to increase cornering speed, improving localization, and then a little idea that we had was to be able to we can control the car manually with the Logitech controller, but if we were able to control it with a sim racing wheel and pedals, that would be really cool as well. And not included on the slide, of course, but something that we found that was quite a funny little thing was that since it is not a it does not have any dynamic response to any obstacles coming in front of it. It could be it could be a military vehicle as well, because we did almost run into people quite a bit, and the car does go quite fast sometimes whenever it's just going in a straight line. So there is a bit of a defense portion of it that could work very well with the vehicle. In conclusion, we were able to accomplish most of our goals. This project was pretty time consuming and pretty taxing all the way around, but I know me and my group members worked quite hard on this, so we were pretty happy with how it turned out. Um, there was a lot of hours put into this car, and there was a lot of time and effort put in by every single one of us. So, despite the design differences and a lot of the components that we used, we were able to reach our end goal regardless of how difficult it was.